All right, welcome to day 9. You can be writing day 9 problems down in your planners. Also, there's a bonus problems on the calendar, which will be due on day 12. You can have those on a separate sheet of paper. We're going to pause the video for 3 minutes for you to check your homework answers. If you didn't get them correct, see if you can figure them out within your group. And then we will go to the worked out solutions, and you can pause for about 45 seconds on each if needed to see the worked out parts. While you're checking your homework answers, the sub will be passing out 2 things. One, the review sheet for the test, the blue review sheet, and also our notes packet for today. All right, we'll go to each homework slide. The sub can pause it for like 45 seconds or so for you to check answers if needed. If no one needs those ones, then we can move on. So when we go to the slide, just yell out pause and the sub can pause the video. So this is 10, 11, and 12. Here's 13, 14, 15, and 16. There's 20, 21, and 22. '23, '24, '25. '27 and '29. So 29 was probably a difficult one. So you ended up cycling when you do L'Hopital's rule twice. It takes you right back to the beginning when you neaten it up of x over radical x squared plus 1. So L'Hopital's rule did not work here, so therefore we needed to do this algebraically. You saw last year with Mr. Deland, square root of x squared is the same as saying absolute value of x. So this original would be the same as the limit as x goes to infinity of x over absolute value of x. The reason being the x squared in the denominator is what will control the value, but when you take the square root of it, it's absolute value of x. Because we're going to infinity, the absolute value of x is the same as just an x, so we end up getting 1 for that. There's 33 and the first calendar problem. And the second calendar problem, I'll talk through this one so we don't need to pause. I'm guessing there'll be some questions on it. So they gave us the original differential equation. So to be in the form that we want, we need the inside to be just our carrying capacity minus whatever our y value is, which is r in this case. So we had to pull a 1 over 200 out front. When you did that, that made it be 1/50th r, and then we're left with the 400 minus r. Again, we needed to do that so that we could identify the carrying capacity, and it also allowed us to identify k in this case. So our carrying capacity was 400. When we do minus that carrying capacity times k, we get the negative 2 in front of the t and the exponent there. We then want to do limit as t approached infinity. So in that exponential part there, we end up going to negative infinity. Well, when you have an exponential that goes to negative infinity, that approaches 0. So the be to the minus 2t approaches 0, so we really approach just 400 over 1, or in other words, 400. Now for the second part, the readership is growing the fastest when there's an inflection point. So we want to take the derivative. Now I first distributed right up here. So that's our original rate. Then I took the derivative, and we needed times dr over dt, and then I just pulled that out of each of them. That's what we got here. You can then replace dr over dt with what we had originally, and I put the factored form in because we would want that factored. So we get 200, 0, and 400. And our inflection point, we switch from a plus to a minus at 200. So the inflection point is at r equals 200 since the sign switches in the second derivative. So we're growing the fastest at r equals 200. All right, remember the email I sent you, it's probably been a couple weeks now, but tomorrow will be day 10. You need to have watched that link, watched that video by class time tomorrow. We'll be talking about it in class. It'll help you wrap your head around what we're going to do. All right, so first off, look at your review sheet that you got. There are two things that I need you to fix on it. First one is that you can cross out question 9. Okay, that's one of those type ones, the partial fraction ones that are not on the AP. So I don't want you to spend time doing that since it's not what would be on the AP. So you can cross out question 9. And then I need you to fix the answer to number 12. The answer should be negative 1/18th, not negative 1/54th. So again, we're crossing out question 9 altogether, and the answer for number 12, you're switching to negative 1/18th. It should say on there negative 1/54th. We don't want that. We want negative 1/18th. All right, so in our notes packet, when we see this integral, if we were to get it on a quiz or a test or something, you might think, okay, I'm going to rewrite this as x to the negative 2 dx. And if you do your antiderivative, that would be negative x to the negative 1, going from negative 1 to 1. Well, if you sub in a 1, that's going to give us a negative 1. Minus, and when you sub in a negative 1, you'll get negative 1, but then it's negated, so positive 1. So we'll have negative 1 minus 1, which gives us negative 2. So we get an answer from doing our process, okay? But if we think of what the graph of 1 over x squared looks like, it looks something like this. The graph is entirely above the x-axis. So that means any area underneath should be represented as a positive number. So even though we got an answer here, this answer must be nonsense. And why did this happen? Well, it goes back to our fundamental theorem of calculus, which gave us this process for evaluating integrals and giving us the meaning of it. If we go down to the bottom of the first page in the notes, our first fundamental theorem of calculus said that f had to be continuous on our closed interval AB. Well, it's pretty clear to see in our graph of 1 over x squared, it is not continuous on that interval. We have an asymptote at x equals 0. So therefore, our first fundamental theorem of calculus did not apply for these integrals. So we need to learn something new so that we can evaluate this. Up till now, we could only evaluate these integrals if x was continuous on the closed interval a to b. But what if it's not? If we go down to the bottom of the second page, there's 3 types of things that we'll work with, and these are called indefinite integrals. Case number 1. If at a or b there is a vertical asymptote. So we see that on the left there. At a there's a vertical asymptote. The graph is approaching it and going up along it. Case 2. If a or b is actually going on forever. So here we want to keep finding the area forever, starting at a and going forever to the right. And then the third scenario is what we just saw in the previous problem. We have an asymptote somewhere in the middle of our interval. So these are all considered improper integrals. So if we go to the third page, we say that the area underneath our curve converges if it is approaching some finite number. And then we go ahead and we calculate that finite number. But if the area approaches infinity or has no limit, then we say that it diverges. So when we're solving improper integrals, if we get a number back, that's really just the number that it's approaching. It's the number that it's converging. If we get some infinity back, then we would say that it diverges. So our first example, okay, if you're in a car, you're going along at 100 feet per second, and at time 0, you take your foot off the gas and you let it start to coast. We have a function representing our velocity. We want to find the total distance traveled by the car. So there's our velocity function there as a graph. That velocity, based on the equation, is never going to equal 0. The velocity is going to get closer and closer to 0, but never hit it. So we're dealing with case 2 here, the one in the middle. We're starting at x equals 0, and then our b value is going on infinitely. And that's why we get this integral here. So start at 0, go to infinity, and we want to see if we can evaluate this. So if we go to the next page, there's some more space for it. The technique that we use is we turn this into a limit. So we're going to make that infinity be a b. So we're going to have this go from 0 to b, and out front we're just going to say this is the limit as b goes to infinity. And then we'll rewrite our integral. So essentially, this is what this is going to do for us. It's going to find a bunch of finite areas as b gets enormous, and whatever it seems that's approaching, if it is approaching something, we'll be able to determine that. So we can do a little u substitution here. So we'll let u equal negative 0.1 t. Our dt would be equal to du would be equal to negative 0.1 dt. We have a positive 100. So we could have either pulled that out front ahead of time, or if you multiply both sides by negative 1,000, that'll give us the 100 and the dt. So if we rewrite, we got limit as b approaches infinity. We've got that negative 1,000 out front now. We've got our integral, and we'll adjust the bounds in a second. And we now have e to the u du. And again, we could have pulled the 100 out front and then just multiplied in our u on du by a negative 10, and that would have done the same thing. So our bounds now, if we sub 0 in for t in our u, we get back 0 again. But if we sub in b, we get negative 0.1 b. Okay, and that's just redefining our bounds in terms of u's. So we'll take our antiderivative now. This becomes limit as b approaches infinity. We'll have negative 1,000. And we'll just have e to the u going from 0 to negative 0.1 b. So we'll fill in. We got limit as b approaches infinity. We've got negative 1,000. This will be e to the minus 0.1 b. Then we'll have minus a minus, so it'll become plus 1,000 e to the 0. So this is limit as b approaches infinity. We've got negative 1,000 e to the minus 0.1 b, and e to the 0 is just 1, so this is plus 1,000. And now we will evaluate our limit. So e to the negative 0.1 b. As b becomes enormous, the exponent becomes a big negative. So imagine an exponential function. As you go far to the left, so if you imagine that exponent is becoming a big negative, we are approaching 0. So this whole part is going to go to 0. So therefore, our integral is approaching 1,000. And our units, we had feet per second, so this would be 1,000 feet. So if we took our foot off the gas and let it coast, we would approach 1,000 feet for the distance that we would travel. So if we go to the bottom, we're going to do the same problem, but we're going to do it with a different velocity function now. So we're going to go 0 to infinity. We got 400 over t plus 4 dt. We'll rewrite this as the limit as b approaches infinity. We have the integral from 0 to b. And if you want, we can throw that 400 out front and just make this 1 over t plus 4 dt. We can do a little u substitution. U will equal t plus 4. du will just equal dt. So this will be limit b approaches infinity. We'll have 400. Our new integral bounds will be 4 and b plus 4. And we'll have 1 over u du. Now, you might not need to do that u substitution. You might be comfortable with that it's just correcting by multiplying by a 1, so that's not really going to affect anything. So it's up to you if you want to do that u substitution. So we'll have limit as b approaches infinity, and we'll have 400 ln absolute value of u, and we're going from 4 to b plus 4. So this will be limit as b approaches infinity. We'll have 400 natural log absolute value of b plus 4 minus 400 natural log of 4. And now we'll evaluate our limit. So as b goes to infinity, our natural log, the inside, is going to become enormous. So we need to be comfortable with what a natural log graph looks like. As b goes to infinity, it's going to grow slow, but that natural log is going to keep growing. So therefore, this value is going to approach infinity. So if that first one's going to infinity, it doesn't matter what we're subtracting off. That's going to grow without bound. So this will go to infinity, and because it's not a finite number, we would say it diverges. So essentially, if this was our velocity function, our distance traveled is not going to approach some value. It's going to keep going, essentially. Okay, so we saw two different cases here. A case where it does converge to a finite value, and a case where it does not, so we would say it diverges. All right, here's our next one. It's the top of the second last page. So we would recognize that this is an improper integral because our b value is infinity. So we'd have limit as b approaches infinity. We'd have integral pi to b of sine of 2x dx. Now, we could do this as a u substitution, but based on what we did with our sine squareds and cos squareds on that day, we're probably okay that it's just going to be a correction by a half. So if we do our antiderivative, we'll have limit as b approaches infinity. We'll have a negative 1/2 cos 2x. And again, where that's coming from, the antiderivative sign is negative cos. And if you did a u for the 2x, you would have du is 2 dx. You'd have to correct by a half. Okay, so just we've seen that pattern a lot, so that saves us a little time. If you wanted to do the u substitution, you're more than welcome to. So this would be negative 1/2 cos 2b plus 1/2 cos 2 pi. Oops, 2 pi, not 2x. Cos of 2 pi, we can figure that out. Cos of 2 pi is just 1, so this is plus a half. So we've got a negative cos graph. It's got a frequency of 2, okay, but that doesn't really change too much what the cos graph is looking like. So if you imagine that cos graph, it is not converging to something. Okay, it's going to be periodic, it's just going to go back and forth. So while this is not going to infinity, it is not going to approach some single value. So we would have to also say that this one diverges. And if you wanted to add, you could say since it is periodic. Okay, so since it'll oscillate between that -1 and 1, it is never going to approach some value. So this is a second scenario you could see that could cause diverging. All right, next example. We would hopefully recognize that this is an improper integral because of that infinity. So we would first want to rewrite this as limit as b approaches infinity. We'll have 0 to b of x squared e to the negative x dx. So we would maybe think u equals -x, but then du is -1. That's not going to help us with the x squared. So we've got a product here of mismatched things. So we want to think integration by parts. We do not have logs. We do not have inverse trig. So our u would want to be polynomials. The u would want to be the x squared. Our dv would be the e to the negative x dx. So du is 2x dx. When you do the antiderivative of e to the negative x, technically we'd have to do a u substitution, like a u equals -x, du is -1, so we need a correction by -1 out front. Because if you did negative e to the negative x's derivative, you would have to multiply by a -1 because of chain rule, and that would make it then be the positive. All right, so let's rewrite this. This is now limit b approaches infinity. We'll have uv, so we'll have minus x squared e to the negative x, minus v du. Well, the v had a negative in it, so this will really become a plus. I'm going to pull the 2 out front, and we'll have the x e to the negative x dx. So again, the negative from the v and the 2 from the du got pulled out front. Well, this is again a mismatched product. So let's do integration by parts again. We can let u equal x. dv would be e to the negative x dx. So du is just 1 dx. And v again would be minus e to the negative x. So we'll have limit as b approaches infinity. We'll have minus x squared e to the minus x plus 2, start a parenthesis. This will all have to go inside. Our VU will give us minus x e to the negative x. We have a minus and a 1 essentially that we can pull out, so this will just be a plus. And we'll just have e to the negative x dx now. And this is something that we can handle. So this will be limit b approaches infinity minus x squared e to the negative x. So we're going to do two things at once. This thing's antiderivative, we've seen it a few times in this problem, is just minus e to the negative x. So we're going to do that and distribute the 2 at the same time. So I have minus 2x e to the negative x, and we'll have minus 2e to the negative x. And I actually, if we go back, I forgot to carry down our bounds each time. Sorry about that. So we'd have 0 and b here. We'd have 0 and b. So this needs to still be evaluated from 0 to b. So we're going to have limit as b approaches infinity. We'll have minus b squared e to the minus b minus 2b e to the minus b minus 2e to the minus b minus parenthesis. If we put in 0 to the first term, we'll have 0 times an e to the 0, which is 0. Second term, we'll have another 0. But third term, we'll have a negative 2 times e to the 0, which will be negative 2. All right, as b goes to infinity, this first one will be a negative infinity times e to the negative infinity. If you think of the graph of e to the x, when you go to negative infinity, that goes to 0. We saw the other day, any infinity times a 0 is an indeterminate form. We're going to have to work with that off to the side. We'll come back to that. This middle term, it's going to also be a negative infinity times a 0. We'll come back to that. This third term, it's just negative 2 times e to a big negative. Well, that part is just going to go to 0. So we know this one's 0, and then this is going to be a plus 2. So this one and this one, we need to work with off to the side because it's an indeterminate form. We saw the other day that we want to try and rewrite these as quotients. The one for negative b squared e to the negative b that naturally goes to the denominator is the e to the negative b. So let's rewrite that first one. We're doing limit as b goes to infinity, and let's write it as minus b squared over e to the b. Okay, so all we did is rewrite it, and the reason we knew to rewrite it is because it was one of the infinities times a 0. We don't know which one is going to their thing quicker, so we don't know which one's going to control the value. So if you have a minus b squared and you go to infinity, that's going to go to minus infinity. An exponential when you go to infinity would go to positive infinity. So this is a L'Hopital's case. So we'll do limit as b approaches infinity. We'll have minus 2b over e to the b. We'll do it again. We'll get a minus infinity on top, infinity on the bottom. That's another L'Hopital's case. So this becomes limit as b approaches infinity. This will now be minus 2 over e to the b. So this is going to give us minus 2 on top. It's going to go to infinity on bottom. So as your denominator gets enormous, this is going to approach 0. So this first spot we know is 0. Now, this second one is an indeterminate form. We need to think about rewriting it as a quotient. But if we rewrote that as a quotient, it would be negative 2b over e to the b. Well, notice that's what we had right here. So we actually already kind of figured that out. It's going to be the same thing there. It's just going to be 0. So if we carry everything down, this will converge. It will converge to a 2. Now, you need all of that analysis to get full credit. Okay, if you just incorrectly said, oh, negative infinity times a 0 is a 0, okay, that's not enough. You need to have some type of work, okay, working with our indeterminate forms to show that that is, in fact, 0. All right, one last example for today. If we go to the last page. R is the region between our curve there and the x-axis. We want to find the volume when it spins over the x-axis. So we want to think disks, washers, or shells. Because the region is completely resting against the x-axis, we would want to do disks. So we would do pi integral sum radius squared. Well, if we're going around the x-axis, we want our slices to be perpendicular to what we're rotating around. That's slicing the x-axis, so we would have dx. The problem is, though, our x values go from negative infinity to infinity. And we haven't seen how to work with it when you're going without bound in both directions, only in one direction. So what we can do is notice that this is symmetrical at the y-axis. So to the left and to the right, they're exactly the same. So instead of doing this integral, let's change this to a 0, and we'll just double it out front. Okay, because whatever the area is when we're going 0 to infinity, the entire thing must just be double that. Now inside here, our radius is just a y value, because it's a vertical line coming up from the x-axis. So that's our initial setup. We need to rewrite this without the infinity. So we're going to have limit as b approaches infinity. This will be 2 pi integral 0 to b. We can neaten this up a little. When we square it, we'll just get 1 over x squared plus 1 dx. So that is an antiderivative rule that we have. Hopefully you recognize that. That's arctan. And we're going from 0 to b. So we'll sub in. We'll have 2 pi arctan of b minus 2 pi arctan of 0. The radian measure that will give us back a 0 for tan also happens to be 0, so that spot is just 0. So essentially, we've got to see what does arctan equal as the b value approaches infinity. Well, here's regular tan. Tan's graph looks something like that. When we switch the x's and the y's, these will now be pi over 2 and negative pi over 2. And our graph will look something like that. Okay, remembering what this arctan graph looks like, it'll come up a decent amount. So that'll be helpful to remember. So as b goes to infinity, so when we go far to the right on this graph, what do the y values approach? Well, the y values approach pi over 2. So this is really 2 pi times a pi over 2, which will just give us pi squared. So this does converge, and it converges to pi squared, which is kind of interesting that that area under that curve will just approach pi squared. So that's it for day 9. Any time left in the period, you can begin working on the homework or your problem set that is due on Friday.